Legend has it that Glastonbury was the seat of King Arthur, and even the resting place of the Holy Grail. What's less well known is that until recently, it was also the centre of a healthy printing industry. Local authoress Frances Howard Gordon has just published a guide to local myths and legends and wants a properly printed press release. Normally, getting a manuscript set into type by a printer is expensive and time-consuming. But a new cottage industry based on the microcomputer has just sprung up in the area.
The copy you've got here is clean enough for us to read on the reader. So, hang on a minute. OK, go. Watch.
An optical character reader does away with the need for retyping. The typewritten page is scanned line by line, and the words are read directly into the microcomputer's memory. Once it's in the machine, errors can be corrected and the text manipulated in a variety of ways.
That's got it all in anyway, but since it's you, I suppose we better run the spelling checker.
Well, don't be rude.
Gog, well, that's the name of that tree, isn't it? We'd better tell it to accept that.
Oh, it doesn't know that, no.
Faces. Oh, you've got another spelling error there. Actors.
Oh.
When the text is correct, the next thing is to choose how it's going to appear when it's printed.
12 point will probably do for main text. And if we go for, say, about maybe 16 or 18 for your heads, what about emphasis, bold or italic?
Bold in the heading, yeah.
So we need this in a larger size, so we'll just call it head.
Once Frances has chosen the sizes and styles of the final print, commands are put into the text to define how each section is to be printed.
We wanted to put all these Glastonbury Maker of Myths into italics. We do that with an instruction which
the machine searches through its memory, and everywhere the word Glastonbury appears in the text, the cursor stops and gives the operator the chance to decide whether he wants to set it in italics or not.
And let's just go and find it in each case. Well, that's one we don't want, so we'll give that one a miss. That's the one we do. So let's go back.
When they're happy with the text, it's sent directly to a photo typesetting machine. Each letter is drawn individually by a flying spot of light onto special photographic paper, ready for printing. So here's Frances's finished document. As you can see, Glastonbury, Maker of Myths, is put into italics. Well, it was only a short document, but a whole book could have been set in type in only a short time using the same system. To carry things one stage further, of course, she could have put her manuscript straight into a word processor and sent it to the printers by post on a floppy disk, or even electronically down the telephone line. But how does a computer handle words? Well, it's important to make a distinction between numbers, on which we can do arithmetic, like the number 12, 2 12s, 24, etc., and strings of characters, by which we mean a collection of letters, symbols, spaces, and so on, such as the word 12, T-W-E-L-V-E. Well, I can best explain this difference by looking at a short program I've got here. We define a variable first equals 12, the number 12. We're going to print it, and then we're going to do a little bit of arithmetic on it, print first plus 1. Let's run it. Well, as you'd expect, it prints out 12, which was the variable first, and then it adds 1 to it and prints out 13. But if we wanted to handle strings of characters using the basic language, there are two things we have to do. First of all, we have to put a $sign after the variable name, and we have to enclose whatever we're going to put into that variable in quotation marks. And we'll write a little program, a new program. And that's a very simple program. We'll do it the same sort of way. First, and we put in the $sign equals, in quotation marks, 12. And we'll print it. Print first, with a $sign again. And if we run that, we get 12 printed out. Now, of course, you can't do arithmetic on variables that are string variables, and it's quite interesting to see what happens if we try. And we'll copy that line, print first, and then we'll add 1 to it, plus 1. And we'll run it. And immediately the computer analyses that we've made a mistake. Type mismatch at line 20. And what this means is that we're trying to mix up a string variable, first with a $sign, with a number 1, which you can't do. But of course you can do certain things with variables, and you can actually use the plus sign. And we'll just copy that command again. Print first plus, and in inverted commas, which means it's a string variable, 1, and we'll run that. And it prints out 12 with 1 added on to the end of it. So what can we do with string variables once they're in the computer? Well, in any decent version of BASIC, you'll remember there are almost as many dialects as there are different kinds of machines. There are a series of commands which are concerned with the handling of strings. Now, we can't go into a great deal of detail, but you can get an idea of how these commands are used if we take an example. Just have a look at these. What have they all got in common? Well, you've guessed it. They all read the same backwards as forwards. In other words, they're palindromes. So how could we instruct the computer to decide whether a word is a palindrome or not? What kind of things would we have to do? Well, let's create a couple of variables, string variables in this case. We'll call one word string, which is the word we're going to put in the computer to test whether it's a palindrome or not. And the next one we'll create is called backward string, which is the word we put in backwards. Now, to get it backwards, all we have to do is to transfer characters one at a time from word string and starting at the end character into backward string and add it on to the end of whatever is in backward string until we've completed all 4 transfers. And then we've created the word backwards in backward string. Then we test whether this word is the same as that word. If it is a palindrome. If they're not the same, then it's not a palindrome. Well, we've written a fairly simple little computer program. It's only got 5 instructions, and we can see how that's done on the machine itself. And here it is. Well, you can see the first instruction, input word string, is asking us to input the word we're going to test whether it's a palindrome or not. This is the basics of the program, the loop, which is going to move character by character the characters from word string into backward string. And what it takes is for place equals len word string. That's the length of word string. In our case, it's 4 characters long. We're going to start at the 4th character. That's the end of the word. And we're going to go backwards. So we go in steps of -1. And each time we get to next place, it will subtract 1 from the 4 we had and loop around this loop 4 times. This instruction 30 is an intriguing instruction. And what this is going to do is actually carry out that move. And it knows what to move by this function here, mid-string. And all this says is, take the character which is 1 character at a time from the position place. In the first case, it's 4. So take the 4th character, one of them, from the word string. And it will carry around this loop, subtracting 1 at a time, until it's done it 4 times. So let's look at that, how it works in practice. Well, first of all, we input the word into word string. There it is, Adam. We then take from position 4, 1 character, and place it into backward string. We then go round the loop again to next place, subtract 1, so place becomes 3, and we end up here on A. And we take the 3rd character, puts it again, adds it on to what's already in backward string. It will then subtract 1 again, take the 2nd character, add it on to what's already in backward string, and finally the last character, and add it on to what's already in backward string. So we've created the word in backward string, which is our original word backwards. And all we have to do is to test whether that word is the same as that. And there is an instruction, if backwards equals word string, then print word string is a palindrome, else print word string is not a palindrome. So let's run it. It's asking me for the input. I'll put in Adam, the same words we had before. Adam is not a palindrome, which we know. So let's run it again. Try another one that we know is a palindrome, madam. Madam is a palindrome. Fine. Let's run it again. And this time we'll put in a rather intriguing little palindrome. Madam, I'm Adam. Now, we might imagine that that is a palindrome. In fact, it looks like a palindrome to me. But to the computer, it says, Madam, I'm Adam is not a palindrome. And that's simply because it treats strings of variables, whether it's a space or an apostrophe, exactly the same as an M and an A. And if you look at that very carefully, including the spaces, it clearly isn't the same backwards as it is reading it forwards. Well, you might like to write a little program yourself that ignores the spaces and punctuation marks. Well, it's just a bit of fun was that program, but handling strings of characters is one of the most useful things that a computer can do. And it's the key to word processing. And we set up our machine here as a word processor, and by that we've put in a word processing package in the machine. In this case, it's stored on a chip inside the machine. We could have stored it on disks or even on cassettes. The extra piece of equipment got to our normal layout, of course, is a printer on which we're going to print out our letters. So let's load the letter in, and loaded in from disk, and there it is on the screen. Of course, this is only an example, it's only a rough idea of what a letter, but it gives us some idea of the sort of things that any word processing package would do. Well, first of all, we want to put in the real name here. So we position the cursor itself, that's the flashing line, using the cursor keys over where we want to start typing. Dear, and we'll call it to Mr. Briggs. That's that. There's a spelling mistake down here. There is R-H-E, and to correct that we can again overtype it and simply type a T. And we've got equipment here and equipment here and equipment there. In fact, I'm writing a letter about a printer, so I might like to replace the word equipment with the word printer. And all I do is type replace equipment with the word printer. I'm such a bad typist that I think a word processor is absolutely brilliant for me. Replace. There it is. And this will position a new cursor over the equipment, and we say, yes, we want to replace that by printer. The second one, yes, we'll replace that. The third one, no. And the last one, yes, we'll replace it with printer. So what else do we want to do? Well, we're writing about a printer. We have a brochure, so perhaps we want to add something to that paragraph there. And we, again, can add something. And I will say the printer contains several advanced features, and I am sending you a brochure. That's fine. And look at it again. Well, I still don't like it completely. I'd like to move the whole of that paragraph up here in this space here, so my brochure comes at the end. And to do that, we simply position a marker at the beginning of it, and then move the cursor to the end of the paragraph, position another marker there, and then move the cursor to where we'd like it to be sent, and move the paragraph, and instantly it's moved around. Well, that looks pretty good, but I don't like the look of this right-hand margin. It'd be quite nice to straighten all that up. So I can take the cursor to the top of the screen, and there's a special key here. I can just bring the cursor down, and paragraph by paragraph, it will straighten them all out. And there it is. So what I want to do now is to save that, and I'll save it, I'll call it letter 2. And that will save it on disks. And then finally, to have a look at it and send it off, I'll print it out. Print letter 2. And there it goes. Well, this is the sort of quality printer you'd need for writing letters. But the other important use of a printer is when you're writing a program, and you can get away with something a bit less expensive. Well, this Sinclair machine has a small printer on it, and we've written a sort of version of our palindrome program, and we could print that out. And there it goes. Well, so far, we've only been looking at the principles of writing short programs. But when you write longer programs, not only is a printer almost essential, but there are some new techniques to be learned. Going shopping in a familiar environment like a supermarket seems very easy, compared with writing a long, complex computer program. The outline is very straightforward. You write out a shopping list, you go to the supermarket, you select the goods that you've got on your list, you pay for them, you go out and you go home. But imagine writing a program for a computer-controlled robot to do exactly the same thing. The actual actions that you go through within the store would have to be broken down into very, very carefully defined procedures, and the robot would have to know exactly what steps to do things that you, in your shopping trip, take for granted. But one of the procedures that we all use is what I call the best buy procedure. And you can use it for buying, for example, toothpaste. Some people buy toothpaste because they like the flavour, but I buy price per unit volume. So I simply take the toothpaste, look at the price, look at the volume, so many millilitres, divide the price by the volume, select the next one, divide the price by the volume. If that is cheaper than that, then I select this one. But that procedure isn't only useful for toothpaste. It can be used for almost anything that you buy by weight or by volume. But there are a couple of other procedures we take for granted. First of all, there's the counting one. I want to buy 3 avocados, so it's 4. Avocados 1 to 3. Select avocado, place in basket, that's 1, next avocado. Select avocado, place in basket, that's 2, next avocado. Select avocado, place in basket, that's 3. And we've got 3 avocados. But it's not every time we want to do it by counting. Sometimes we want to buy by weight. And there we want to buy a pound of tomatoes, so we have an instruction which says, repeat, place tomato on scale until scale greater than 1 pound. So we keep on repeating until scale greater than 1 pound. And there we have just over 1 pound of tomatoes. Well, those are fairly straightforward procedures, but there's one procedure which, even in a supermarket, is very complex, and that's at the checkout. Well, this is one situation we've all been faced with: how to get out of here in the shortest possible time. Well, I guess a procedure would go something like this. If there's an empty lane and it's manned, then select that lane. Else, select the lane with the shortest queue. Well, if there's more than one lane with the shortest queue, then select that lane where the people have the smallest number of goods in their baskets. It's quite complex, and you might get it wrong, and it doesn't account for how fast the teller is. Well, fortunately, I'm lucky this time. Hello. Well, that was pretty easy. And one thing's absolutely for certain: it'll be a long time before you see any damned robot able to do it. It's a great game. Absolutely marvellous. I know somebody who plays it with a very low technology pack of cards. Well, that game was written by Ian Trackman, and he's written most of the programmes both in this series and the previous series of the computer programme. Ian, how do you go about writing a long programme?
There's 3 parts to writing a programme: analysis, design and coding. Analysis means working out what you want the programme to do. In this case, what are the rules of patience? When you write a commercial programme, very important, what does the client want out of the computer? When you've worked out what is wanted, you then move on to the design stage. Design, well, besides simply designing the screen, it also means working out the parts of the programme, breaking it down into these logical blocks. That's what we call structuring, structured programming. Only when you've done that, then, can you move on to coding, and that is typing in the words in BASIC, whatever language we're using, as we've been seeing in the little programs.
Well, how long is the BASIC? Is this patience program?
Well, I've got here a listing of the program that I've taken off the printer, and it's a reasonably sized program for a microcomputer. There. And let's go back. The interesting part of it is actually the beginning here, because there's the main part of the program, and I've marked with these red lines the procedures, the blocks, logical blocks that I've broken the program down into, and there's about 20 or so of them. The main part of the program calls a few of those procedures, and they in turn call other procedures. And for instance, here's one, I've called it proc bell. That's the one that makes a noise when you turn a card over or you make an illegal move, something of that sort.
So it starts with define procedure bell, it goes through till it ends procedure, and every time you refer to procedure bell, it goes to that and runs it for you.
That's right, and then it gets to this end proc. When it gets to end proc, it goes back to wherever it was called from and carries on with the rest of the program.
I see, yes. Well, what's the difference between good programming and bad programming?
First of all, as far as the programmer is concerned, a good program is one that is well structured, it's well laid out, it's easy to follow, it's easy to find the bugs, and particularly again in a commercial program, if the client wants it changed, how easy is it to go back to it and make a change to it? And then the other part of the answer is, from the user's point of view, what's a good program? Well, it must be a program, first of all, that you want. I mean, as you quite rightly said, with patience, you've got to decide you want to play it on a computer or should you just play it with a pack of cards in any event. And then it's got to be easy to put information into the program off the keyboard or whatever we're using. It's got to be easy to see what's going on, and the output, the presentation, has got to be clear and helpful.
And it shows the difference.
Well, again, here I've written a couple of programs. The first one is a good program, and let me put that into the computer now. We'll load it up. First thing is it sets out the screen nicely. It asks, would you like to see the rules of the game? Please press Y or N. Well, I'll explain the rules to you, so we won't press yes. Just before I do, though, let me just show you. If you press K or F or S or anything else, it's refusing it. So we'll press no, and we're straight into the game. It's a very simple little game. We throw dice on the screen and press to stop. The dangerous throw is 2. That means we keep on playing until we hit another 2 or we decide to stop. If we hit another 2, we lose all the score in that round. So at the moment the computer is playing. Let me think, it says. Yes. Let me think. Again, it's going to have another throw. Again, it's going to have another throw. It's decided it's going to take its chances here.
Well, it's throwing a 2 and the chance of throwing a 2 is very low.
Yes, so we'll let it go on for a long
Yes.
time. It will continue running. Eventually it will decide to stop, and then it's our go. So the important thing about this is it's well presented, it's interesting to play, it looks good. Let's compare that, shall we? I've also written the same programme, but I've tried to write it as badly as I can. So we'll stop that, and let's load in the bad version of that programme.
Was that more difficult to write than the good version?
About as difficult. Look at this. The first thing is it didn't even clear the screen. It's got instructions down the bottom of the screen here. Well, let's see what happens. If I type in Y, expecting instructions, it doesn't give that to me.
Straight into playing the game.
Because, well, I've put in the program, it will only accept YES, but there's no clue to that on the screen. Straight into the program. Still, look at this. It's no space between round and 1. It's messy. Well, we'll say yes, we will have more. And look, it's a horrible mess. I mean, I wouldn't play that at all. Just no good at all.
What about in the writing of the program itself? How would they differ?
Again, we would break down the good program into these procedures we've been talking about, so the whole thing is set out logically. Here's the listing of this bad program. Now, it's fairly short, but then who wants a short program that's rubbish? What I've done here, I've joined together all the different routes the program can take, and you can see that's a terrible mess, ever so difficult if we have a bug, a mistake in it, to find out where it's going wrong. And this, for obvious reasons, we call spaghetti programming.
If you have a bug in a structured program, you know it's in one particular procedure, so you can go to that procedure and correct it. In that, it would be a nightmare to try and sort out just what
it would
happened.
take me probably longer to find a bug in this than it would in the big, well-written program.
So have you got 3 tips for somebody of how you write a good long program?
Yes. First of all, decide what you're going to write. Then decide how you're going to write it, and only then get on and put it onto the keyboard.
Thank you, Ian. Well, as we've seen, modern computers can not only do calculations and handle words, they can also display graphics. Well, next time, we'll begin a look at the world of computer graphics and animation.